Welcome. My name is Professor Banks. I have been given the opportunity to share with you alumni some of my research in this very short presentation. So let's cut to it. I've entitled this presentation, short presentation, Enabling Advanced Simulations with Mathematical Analysis. As I said, my name is Jeff Banks. I'm Associate Professor and also the Eliza Ricketts Career Development Chair. So what do I mean that we're enabling simulations using mathematical analysis? Well, it's really the analysis which underpins all of my work. So our research focuses on using analytical tools from mathematics to construct new algorithms that can solve problems which we couldn't solve previously. So for example, here's an example. I have this funny geometry, which we call this starfish geometry. And the idea is I put this starfish geometry inside of a high-speed flow. And the thin black lines that you see running around here are all shock waves. Now the key point about this starfish body is that its mass is 0. And so if you just think back, the basic equations governing the motion of a rigid object are F is equal to ma, or you could say F is equal to m times the time derivative of v. Well, the trouble is if the time derivative of v term goes away because the mass of the body is 0, all that's left is the F on the right-hand side. And so it doesn't appear possible to address the simulation which I've presented simulation results for. But the mathematical analysis actually tells us how this is supposed to work. And what happened is it turns out that the MVB term does in fact go away, but what's left is this term here, which has exposed how the force depends on the mass of the body. And so what we have done is enabled the dynamical equations to tell us how this object moves, even though it has no mass. And this resolves an open problem from the times of even Love in 04 and Taylor in 42. So we take those algorithms and we apply them to cases which have potential application with real impact on, for example, patient outcomes in this case. So we want to be able to address how blood flow is affected by an artificial heart valve. In this case, here is an example heart valve. And here is a computation on the left that we set up to mimic what's happening here. Now, if you have an artificial heart valve implanted in you, what you don't want is clotting. Clotting is caused by high regions of shear stress. And so we can analyze now the effects of various mechanical changes and changes in design on the heart valve with our tools in a very efficient way and hopefully positively impact people's lives, patients' outcomes. A second example comes from the field of so-called metamaterials. So this is an example from the web of a flat lens. So a flat lens for optical light can be constructed by imprinting these very small pillars and H's and dots. Those are actually gold, which has been imprinted on a substrate in a particular pattern, and each one of those pillars has a particular geometry. Now on the bottom is a simulation we've done of that geometry using electromagnetics going through it. The idea now is that you can use our tools to help in the design of where to place these various objects in order to make a lens in this case that you could not make if you used only naturally occurring materials by themselves. For example, you cannot make a flat glass lens. It just simply won't work. But with these metamaterials, you can do so. So our work is associated with the Center for Optimization, Computational Analysis, the MOCA Center, here in the School of Science. And as always, we like to take pride in RPI. And for example, here are some fun simulations that we've used in various publications we've had on the topic. So on the left is FSI, fluid structure interaction problem, using this RPI geometry. So this is an incompressible flow. This appeared in the Journal of Computational Physics in 2019. And then on the right, we've done an electromagnetic propagation through RPI, again appearing in Journal of Computational Physics in 2020. Thank you very much for the opportunity.